Oh yeah. Feels like
I know.
You went to the back already.
Yeah. Oh my god, they're gonna see. Oh.
Yes, it is still 14.1. Okay, so, yes. Okay, what?
Kelly, you're very slow.
Alright, could we start already? I didn't know that Alia now has a duty to distribute sweets. Okay. It was meant for you all to stand up and then go take a walk. Alright, shall I start? Okay, Alia, you can just sit down. No need to distribute the sweets. Okay. Alright, so yesterday, okay, so Cheng, are we ready? Are you okay? Alright, yesterday we talked about stationary points. So there are three types of stationary points, okay, your maximum, minimum, as well as point of inflection. Whereas if you use the term turning points, then it is only limited to just maximum and minimum points, okay? So that was what we first mentioned yesterday, right? That there are maximum, minimum, and point of inflection. Okay, so these are what we call stationary points. Then yesterday we looked at how the first derivative test could actually help us to determine stationary points. Okay, whereby in the first derivative test we need to draw out the table. Okay, so for the particular x value that we are looking at, let's say it is a, we look at smaller than a and bigger than a. Then we look at the sign of dy dx. And then we draw the tangent. Okay, so that will be how we identify stationary points. Then at the very end of the lesson, we look at second derivative test. Okay, whereby we look at the second derivative, which we call the 2y over dx squared, if we were to use this notation, where if it is more than 0 in value, okay, we can relate it to how we see our quadratic curve in terms of a happy face, because positive things make us happy. Then after that, it will give us a minimum point. Okay? And then if you were to look at the second derivative again, and if that is negative, okay, we think of negative stuff that will be sad. So sad face, so maximum point. Okay? Second derivative test does not tell us whether is it point of inflection or not. Later on, I will give you an example that shows us that second derivative, if it is equals to 0, it does not tell us that it is point of inflection. Okay, so those will be the examples that we're going to cover today. Right? So let's practice using our second derivative test first. So by looking at try 4 in your textbook, page 54. Try 4. Where we have y equals 2x squared minus 16x plus 27. In part I, we want to find the coordinates of the stationary points on the quadratic curve. Okay, so We covered this yesterday. How do we go about finding the coordinates of the stationary points? What is it that we must do? Say, what do you think? Okay, we do the dy over dx, and in this case dy over dx is equals to okay, 4x minus 16, great. After we find dy over dx, what do we got to do? Answer? We want to find stationary points. What is the significant thing about stationary points regarding their dy over dx? Okay, all of it will have dy over dx equals to 0, right? So maybe just plug it here. So 4x minus 16 equals to 0 will help us to find all the stationary points. In this case, there is only 1, and that happens when x equals to 4. We want to find the coordinates, so we got to find a y coordinate. We substitute it back into this equation here. Okay, and we will get negative 5. So therefore, stationary point is 4, negative 5. Okay. Then in part 2, we want to use the second derivative test to determine the nature of the stationary point. So we're looking at 4, negative 5. In the second derivative test, we got to find the second derivative. So in this case, since we know that dy over dx is already 4x minus 16, our d2y over dx squared, differentiate this again, I will be getting a value of 4. Okay? It is not all the time that you will get a constant number. Okay? Very often, in fact, it will be an expression. Okay? So maybe like 4x or 3x minus 7 kind. Alright? So coincidentally, it is actually 4 in value, and 4 is a positive number. So this tells us that, okay, the stationary point 4, negative 5 will surely be a minimum point. So we explain by saying that since the second derivative is more than 0, then 4, negative 5 will be a minimum point. Okay? Right, next we look at try 5. Okay, we want to first find out the coordinates of the stationary point given y equals 6x to the power of 5. and we want to then determine the nature of the stationary point. Okay, so we notice that from try-4, using the second derivative test, it is much easier because we just have to differentiate, substitute a value if necessary. Okay, in this case, I'm not able to show that due to the example. Right, then after that, we will be able to quickly determine whether it's a maximum or minimum. Okay, so in this case, let's do the same thing. Alright, so with y equals to 6x to the power of 5, we find the dy over dx. Okay, and that will be our 30x to the power of 4. Okay, focusing on finding the stationary point, 30x to the power of 4 got to be equals to 0. Okay, and what will the value of x be? It will be 0, right? Okay, so we continue here. With our x to be equals to 0, our y is also 0, so the stationary point is coincidentally the origin. So 0, 0 is the stationary point. We got to write down this statement so as to answer the first part of the question that asks for the coordinates. Okay, so you cannot just leave it at finding y equals to 0. Then to determine the nature of the stationary point, we find our d2y over dx squared. So we differentiate our dy over dx again, we get 120x cubed. Alright? So this is the difference between try 5 and try 4. Try 4 we got a number. Okay, try 5 we got an expression. Right? So since we are trying to investigate, okay, at the stationary point itself, what the second derivative is, we use the value x equals to 0, substitute inside here. Okay, so when x equals to 0, our second derivative will be equals to 0. Okay, and this is where the limitation of the second derivative test happens. Okay, so with the second derivative to be equals to 0, there's no conclusion. Okay, so just a point to note, not conclusive when using second derivative test. Right? So whenever you face a situation where the second derivative test gives you, rather the second derivative gives you a 0, we got to fall back onto our first derivative test. Okay? So then we have to go into drawing the table. So x sine of dy over dx tangent. So we're looking at 0, negative 0.1, and 0.1. Alright, could you key into your calculator now? Tell me what is the sign that you get, okay, for dy over dx. So you substitute negative 0.1 into dy over dx here, right? And tell me what is the sign. Okay? Will you do that now? You press in the calculator. Is this what? Positive? Positive here, right? What about 0.1? Also positive? Okay. So tangents look like this. So it's like an S shape. Okay. Tangents looking like that. And this tells us that it is a point of inflection. So therefore, 0, 0 is a point of inflection. okay, not all d2y over dx squared equals to 0 gives us point of inflection. Okay, so we cannot draw that conclusion, right? It is purely coincidental that in this case you're getting a point of inflection. Alright? I will show you an example whereby it is not a point of inflection when the second derivative is equals to 0. Okay? So, this example that I'm giving you is kind of an edit, okay, from your exercise 14.1, question 4. Alright, I just edit it a bit. I believe you're already familiar with how to do part I. Alright, so could you do part I now? Just give you 3 minutes. Okay. Determine what is the coordinate of the stationary point. So do part I. get 0, 1 to be a stationary point. Alright, so let's look at part 2. Okay, so let's look at the second derivative test. Okay, second derivative test will tell us that the second derivative itself is going to be 150x to the power of 4. Okay, because we differentiate the dx to the power of 5. Alright, so at the point 0, 1, our second derivative will be 0 because x equals to 0 will make the whole expression here 0. Okay, so we go and look at the we look at the first derivative test. Okay, so in this case, coincidentally, it's the same table, so I'll just use this frame here. Okay, so we look at 0, negative 0.1, and 0.1. Okay, so if you substitute in the numbers, what is the sign of the dy over dx that you're going to get? What do you get when it is negative 0.1? Cannot, what do you get? Sorry? Negative, okay. And then if it is a positive 0.1, Joseph, can you tell me what is this? If it is a positive 0.1 into my dy over dx, what do I get? Sorry? Positive. Okay, so we get a positive, right? A positive number. Okay, so in this case, negative, 0, positive, going like that. Alright, so in this particular case, it is not a point of inflection, it is in fact a minimum point. Okay, so just add it from here. 0, 1 is a minimum point. Okay, so this is an example that tells us that it is not all the time that when second derivative is 0, it gives us point of inflection. So no, right? It can be possible to give us minimum point. It can also be possible to give us maximum point. Alright, so you have to actually do your second derivative, then after that do the first derivative test when you encounter a 0, right, in the second derivative value. Okay? Now let's move on. Okay. Looking at exercise 14.1, question 12. Okay, part 1, we want to find coordinates of the stationary point. Okay, part 2, we want to determine the nature of it. Part 3, we want to explain why the gradient of the curve is negative when x less than 0. Okay, at this juncture, I just want to point out that although in this question we also only get one stationary point, okay, it is not all the time that any function there's only one stationary point. Okay, it is possible that in a function there are two stationary points or even more than that. Okay, so don't develop the misconception that there's only always one stationary point. Right? It's just coincidental that all our examples here have only one stationary point. I want you to do part I and part 2 now. Part 3 I'll leave it later on. Okay, so give you about 4 minutes. Alright, do part I and part 2. Yes.
But if you do first test, maybe you can catch it. Because first test is probably whether it's a minimum or small point of inflection. Yes, we don't have to. But the reason why we always fall back on the second derivative is because it is convenient. Yeah, we don't have to draw a table. Yeah, we just go about differentiating. So we find it faster. Yeah. So actually, if you want to, we can always just do first derivative. But of course, it depends on questions as well. Sometimes questions actually specify using the second derivative or using the first derivative. Okay, so we have to look at the question.
Okay. Are we done? Maybe I give you another 2 more minutes. Our answer. What is the stationary point coordinates, Nicole? 3 and 27. Okay. Is it a maximum, minimum, or point of inflection, Amanda? Don't know. Okay. Maybe wait now. Is it a maximum, minimum, or point of inflection? Sorry? Minimum. Okay. So let's check our answer. Alright. Whether is it 327 and whether is it a minimum point or not. As I walked around, okay, I see that many of you, when it comes to differentiating this, you like to do quotient rule. How many of you did quotient rule? Okay. Anybody did anything else? Alright. So, Bobby, how did you do it?
I simplified the x squared plus 54 x.
Okay, you simplify it to x squared plus 54 over?
54 then x to the power x.
Okay, so simplify this into x squared plus 54 x to the power negative 1. That is also possible. Okay, if you had done your revision for your A Maths WA1, right? Okay, in my working itself, okay, when it comes to such questions, when the denominator is only one term of x or x squared, x cubed, and all that, we could actually simplify it into saying it in this manner. Okay, so we get x squared plus 54 x to the power negative 1. You may find that this is maybe slightly easier to differentiate. Okay, although doing it by your quotient rule is not an issue as well. Okay, if you want to do by quotient rule, no problem. Just that maybe sometimes quotient rule might be slightly longer. Okay, so if I were to show you how quotient rule is done, right? So in this case, we keep the bottom, differentiate the top, minus away, keep the top, differentiate the bottom, and then the bottom square. Okay. So when it comes to quotient rule, you just got to remember the routines of it and be very careful of how you differentiate the different parts. Alright, the answer will still remain the same. Minus plus become minus. Okay, so we will be getting this. Maybe some of you don't simplify it, right? You get this answer, that's also fine. Right? But actually you could simplify it such that 2x cubed over x squared gives us 2x and 54x squared gives us this term. So it's actually exactly the same thing. Alright? Now we want to determine the coordinates of the stationary point, so we let dy dx equals to 0. So when it's equals to 0, we cross multiply. So when x cube is 27, we take cube root. Cube root there's only 1, so therefore x is equals to 3. When x is 3, our y will be equals to 27. So therefore 327 is a stationary point. Okay. Now earlier on, before you started the question, earlier asked me a question, okay, whether the nature of the stationary point, can I actually just directly do first derivative test without doing second derivative test? You definitely can, okay? If you don't want to do second derivative test because of the problem that when the second derivative is equals to 0, you still end up having to do first derivative, right? You can go ahead and do that, okay? That means you just do first derivative test only without having to do second derivative, right? So you can do that, but on the condition that the question did not specify the method that you're expected to use. Okay? So if the question says using the second derivative test, then you must only use this. Alright? If the question says using the first derivative test, then you must only show this. Okay? So be careful about what the question demands are. Alright? When you do first derivative test, you no need to go and do this anymore. Okay? But when you do second derivative, sometimes you may have to do this. Alright, so it's up to personal preference, okay? For most of the time, I will always be using second derivative because I find that it is easier to differentiate and then substitute in number to determine the value now. Okay, but of course, personal preference also. Right, so in this case, if I were to do the second derivative test, since we're at that, we will be differentiating this. I will get 2 minus away negative 2, 54, x negative 3. So that is equals to 108 over x cubed. So when x equals to 3, second derivative will be this. Value itself, okay, is equals to 6. Please calculate and tell me what is the value of the second derivative test. Okay, sorry, second derivative. Show that it is more than 0. Okay, then you conclude that since second derivative is more than 0, then 327 is a minimum point. Okay? Questions? Alright. Next, part 3. Explain why the gradient of the curve is negative when x is less than 0. Since we're looking at the gradient of the curve, okay, the gradient of the curve expression is represented by my dy over dx. So the question is asking, why is it that this is actually lesser than 0, because negative, when x is less than 0? Okay, so we target on this one. Alright, let's see, what can I erase? I erase this part, alright? Okay, so when x is less than 0, there are 2 parts to my dy over dx. Okay, one part is 2x, alright? So 2x will surely be lesser than 0 when x is lesser than 0. Okay, then after that, my x squared will surely be positive. Okay, so if this is a negative number, minus away, overall this fraction will still be a positive number. Okay, so it's a negative, you minus some more, right? A positive number. Okay, surely your end result, your dy over dx, will have to be negative. So when this, okay, therefore dy over dx will be less than 0. Okay, So therefore the gradient of the curve is negative when x is less than 0. Right, so this will be the explanation for question 12, part 3. Okay? So that's it for 14.1. Homework. Exercise 14.1 due by 13.4 is by 3rd March, which is here. Oh, you want to take life history, man?
You shut up.
Some take, alright? Otherwise you wouldn't be on this board here. That is odd week. Thursday? Exercise 13.4 here. Then this one, 14.1. Can? Add up. Final call. 4th March. Right, question 3, 7, 8, 10, and 14. Okay. Still got 15 minutes. We can go on to 14.2. Okay, let's move on to chapter 14.2, where we are going to be looking at maxima and minima problems. Essentially, in this section of the chapter, okay, it is just problem sums, okay, and you will be you need to understand the problem sum at the beginning, okay, figure out whether there's a need for you to create an equation. Then after that, use your first derivative and second derivative test also. So our first and second derivative test will form as a basis to our maximum minimum problems. Okay? Okay, in try 6, right? Are we all okay? Too bad, still have to go on. Okay. At least you're seated down, you know. Okay, so let's look at try 6. We are given the x and y are positive numbers. They say that x times y is 20. Then they introduce another number z, such that z is actually x plus y over 5. They want us to show that z in terms of x. So we want to get rid of the y. Okay? So in this part, since we know that xy is equals to 20, our y will be equals to 20 over x. Okay? We substitute this into how z is written. So z is x plus y over 5. We change the y, okay, into 20 over x. take note that if you write a fraction in a fraction, make sure your fraction lines are visibly correctly divided. Okay, so this one should be shorter line, this one longer line. Right? Alternatively, you can also understand it as 20 over x divided by 5. Okay, if you don't want to have the confusion in your fraction line. So we simplify this. So it's times 1 over 5. Cancel 4. And we have x plus 4 over x. So that's shown. Okay, part 2. Calculate the value of x for which z has a stationary value, and show that this value of x makes z a minimum. Okay, so it's quite a confusing question statement. So let's look at the first part that asks us to find out the value of x such that z itself is the stationary value. Okay, so for z to be a stationary value, that means that my dz over dx must be equals to 0. How do I get dz over dx? Okay, I use z equals to x plus 4 over x. I cannot use z equals to x plus y over 5 to determine dz over dx because y itself is a variable. So I cannot ignore the presence of y. Okay, so I've got to make z in terms of x first. Then I can differentiate. So tackling the first part of the question, when z is expressed as this, which actually means this. Our dz over dx is 1 minus 4x to the power negative 2. So we want z to be a stationary value, so dz over dx must be equals to 0. And we find that when we take square root of 4, we got positive and negative. So it's either 2 or negative 2. But then, okay, question specified that x is a positive number. Okay, so we reject. Okay, because x is positive. So we have found the value of x that gives us z to be a stationary value. Okay? Any questions in this section here? Alright? Next, we want to show that this value of x, which is 2, okay, makes z a minimum. Okay, so for z to be a minimum, we use d2z over dx squared. Right? So d2z over dx squared, second derivative test, tells us that it is a minimum. Minimum is a happy face, so your second derivative must be more than 0. So we will show that, okay, second derivative is more than 0. That justifies for us that x equals to 2 creates a z to be a minimum. Okay? So second derivative will be, looking at this one, negative 4, bring down negative 2, x negative 3. So second derivative is our 8x to the power negative 3. we want to see that when x is equals to 2, we determine the value of the second derivative that is equals to 1, which is positive, and that is expected. Okay, we should be expecting a positive number because question asks us to show that it's minimum. Surely that will happen. If end up you get a negative, that means something is not right with your second derivative expression itself. Right? So second derivative, since it's more than 0, okay, we can conclude that therefore x equals to 2 makes z a minimum. Since second derivative more than 0. Okay? So this example over here shows us the efficiency that we can get when we do second derivative test. Okay? Because the question actually in fact told us that surely you're expecting a minimum already. Okay? You will have to negate the idea that you're going to be expecting a point of inflection. So since point of inflection is out of discussion, alright, we can just use second derivative test. We need not go on to our first derivative test. Okay, although using first derivative test is not a problem at all. Okay, but it's not efficient now. Alright? Okay, any questions? Alright, so I'll just leave this at here. Alright, I'll end the lesson here today. Next lesson is our WA1, which is a 1 hour 20 minutes lesson. I know. Okay, it's only 1 hour paper. Okay, is it 1 hour paper? 30 marks, no, 45 minutes paper. Okay, so